Take a moment and look around. You are constantly in motion, but not all motion is the same. What is the difference between simply moving and actually acting? When I reach for a book on a high shelf, or maybe just stretch my arm out to relax, I am acting. I have a purpose. But if my arm suddenly jerks up because of a muscle spasm, or if someone else lifts my wrist, I am not acting. Something is simply happening to me. That distinction is the most fundamental question in cognitive science. It's what separates mere movement from action. Action, at its heart, is purposive behavior. It's any behavior intended to cause a change in the world, or even a change within ourselves. To understand this, cognitive scientists are on a quest to discover the distinctive mental processes, the secret blueprints that our brains use to plan, execute, and control every single purposeful thing we do. And that quest is exactly what we're diving into today. To truly understand action, we have to travel back in time. For centuries, philosophers recognized that the crucial difference between a simple twitch and a deliberate action was purpose. The philosophical quest: what is intent? This idea goes back to Aristotle and led philosophers to think about the concept of intentionality. According to modern philosophers like Anscombe and Davidson, for a movement to count as an action, it must be done under some intention. In other words, if you bump into someone, it's only an action if you did it on purpose. For example, if you meant to bump them, or if you had another goal, like jumping back to avoid a crash, it qualifies as an action. But if you just felt dizzy and accidentally bumped into them, that's not an action. It's simply an event. In the 1960s, this idea sparked a major debate. Are the reasons behind our actions, our beliefs and desires, also the causes of those actions? Davidson said yes. He argued that while there may be many possible reasons for what we do, the specific belief or desire that actually causes the action is the one that physically contributes to it. This way of thinking built a bridge between reasons and causes, allowing science to finally begin studying the mind as a natural system. Meanwhile, the early world of science and psychology had a much simpler but ultimately flawed view. It was called the sensory-motor theory. Think of your body as a simple pinball machine. An outside stimulus hits a sensor, which causes a movement, and that movement's feedback triggers the next movement in a simple chain of reflexes. But this theory quickly failed to explain the most human thing we do: voluntarily deciding to do something new. A scientist named Carl Lashley pointed out that we can instantly learn and perform a sequence of new actions, like typing a sentence you've never thought before. This required more than just reflexes. It proved that action is centrally organized. It requires an internal plan or motor program existing before the first muscle even twitches. This new idea, called centralism, gave us two essential concepts for how the brain controls action. Homeostasis, that is, the internal goal. Introduced by Walter Cannon, this is the brain's way of setting an internal reference point. Think of it like a thermostat. Your brain says the temperature should be 20 degrees. If the input signal says 18, the brain initiates a process to fix the discrepancy. This shows action can be triggered by an internal need, not just an external stimulus. The efference copy, that is, the brain's prediction. This is the ultimate neuro trick. When your brain sends a command to your arm to move, it sends a copy of that same command, the efference copy, to a different part of the brain. This allows your brain to predict what that movement should feel like. It's how the brain monitors its own activity and knows the world is changing because you changed it, not because something happened to you. Today, this concept of centralism is king. As researchers like Mark Generod observed, for us to perform any goal-directed behavior, we must possess internal models of both ourselves and the external world. We need to be able to predict the consequences of our actions, a concept borrowed directly from the world of robotics and control theory. This means that every choice you make is a high-speed prediction game orchestrated deep inside your mind.
What unifies action? Action, as we define it, comes in countless forms. Think about your day. You perform routine actions like brushing your teeth and deliberative actions like planning your next vacation. There are bodily actions like throwing a ball and mental actions like solving a math problem in your head. We even have hot actions driven by emotion and cold actions executed dispassionately. This incredible variety forces a question: is there one fundamental thing that unites my routine drive to work, my mental calculation, and a cat pouncing on a mouse? The problem with intentionality. The simple philosophical definition that an action is a movement caused by a conscious, fully formed intention doesn't cut it. Why? Because that definition focuses too narrowly on human, bodily actions. It fails to account for mental actions, and more importantly, it fails for purposive behavior in animals or infants. A cat pouncing is clearly an action with a purpose, but we can't assume that cat has a complex, language-based, propositional intention like, I believe I will catch the mouse and I desire to eat it. It's still goal-directed, but it's less demanding. The unifying factor: control. Cognitive science realized we need a less strict definition. We need the concept of purposive action, which is often based on non-propositional goal representations, meaning the goal is encoded in a simple motor, visual, or perceptual format, not necessarily in conscious thoughts or language. But whether you are a person planning a trip or a bird building a nest, there is one non-negotiable requirement for action in all its forms. The agent must have some degree of control over what they are doing. They must be able to guide their actions. This is where your brain's high-level command center, the executive functions, steps in. These functions, things like your working memory, task switching, and most crucially, inhibition, are what allow you to maintain, guide, and stop an action to achieve your goal. This ability to exert control is the true core of agency, regardless of the species or the complexity of the task.
The brain's control room. If control is the engine of action, then this next part is the command center. To select and initiate an action, your brain actually runs 3 different decision-making systems simultaneously. These systems often compete or cooperate to guide your next move. Distinction 1. Internal versus external drivers. First, we ask, what is driving the action? Is it internal or external? Endogenous actions are driven by internal motivation. You decide to get a glass of water because you feel thirsty. These are your intentional, voluntary actions. Conversely, exogenous actions are triggered by the environment, like an object in your path immediately triggering you to step around it. This isn't absolute. Intentional actions still need external cues, but neurologically, the split is clear. Your medial prefrontal cortex handles your internal goals, while the lateral prefrontal cortex lights up when you react to the environment. If this control system breaks, you get syndromes like anarchic hand, where one hand acts spontaneously on external objects against your conscious intention. It proves your brain has distinct neural roots for internally driven behavior versus externally triggered reactions.
Distinction 2, goal versus habit. The second distinction is crucial for understanding behavior change. Is your action goal-directed or is it a habit? Imagine a rat pressing a lever for a food pellet. If we suddenly make the food taste terrible, a goal-directed rat will immediately stop pressing the lever. It understands the outcome has been devalued. This relies on declarative memory, knowing the facts and consequences. But if the rat is overtrained, it becomes goal-independent or habitual. The rat keeps pressing the lever even though the food is worthless. The action is now simply a reflex triggered by the lever's presence. This relies on procedural memory, muscle memory. This tells us that even complex human actions, like checking your phone every 2 minutes, can switch from a deliberate goal to a mindless, ingrained habit. Distinction 3, model-based versus model-free strategy. The final distinction explains the strategy your brain uses to choose the best action, and it's borrowed from artificial intelligence. It's the trade-off between flexibility and efficiency. Model-based decision-making, this is like your brain calculating the entire map. It builds a detailed internal model of the world, constantly calculating every possible outcome and trajectory to find the absolute best choice. It's highly flexible, but computationally slow and demanding. Model-free decision-making, this is your brain using shortcuts. It assigns cached, simple value scores to actions based purely on past rewards. It doesn't know why an action works, only that it did work last time. It's fast and efficient, but if the environment suddenly changes, its cached data is useless and it takes time to relearn. Essentially, your brain uses model-based for complex, high-stakes decisions and model-free for rapid, everyday tasks. By constantly arbitrating between these 3 complex systems, internal versus external, goal versus habit, and model-based versus model-free, your brain manages the incredible feat of navigating reality in real time. Once your brain settles on a choice, be it goal-directed or habitual, it's time to move. But there's a massive gap between saying, "I want to drink coffee," and actually lifting the cup. That gap is filled by motor planning.
From intention to blueprint. First, let's distinguish between 2 types of plans. Planning a vacation is high-level planning. It uses complex reasoning about beliefs and desires. Motor planning is completely different. It's the low-level, specialized process that specifies the means to achieve an immediate goal. It's the moment your abstract intention is translated into a physical sequence of bodily movements, like extending the elbow, adjusting the hand grip, and finally grasping the mug. But the motor system immediately runs into a complex challenge called the inverse problem. Why? Because of physical redundancy. Your limbs, joints, and muscles give you dozens of ways to perform any single action. You can reach that mug 100 different ways. The challenge for the brain isn't if you can reach it, but how to select the optimal solution. The path that minimizes effort, reduces discomfort, or maximizes smoothness. Your brain is a constant optimizer.
The dual visual system. This intricate planning process happens in a hierarchy, moving from a high-level goal to the finest muscle control, and it all depends heavily on your vision. To select a target and calculate your movement, your brain relies on 2 distinct neural pathways for vision and action. The ventral stream. This system helps you identify what the object is. That is a mug, not a pen. This is crucial for object selection. The dorsal stream. This system computes where the mug is and how your hand needs to move in relation to it.
It handles the moment-to-moment, fine-tuned visual motor transformations required for the actual action. So your brain uses two highly specialized visual systems to talk to the motor system, one for recognition and one specifically for action specification. We've covered the history, the control systems, and the planning blueprints, but cognitive science is still wrestling with three massive questions at the frontier of action research. Questions that fundamentally challenge what we thought we knew about the mind.
Question 1. How deep does the mind-body connection go? For a long time, we treated motor, movement, and cognitive, thinking, processes as separate systems, but mounting evidence proves they are constantly interacting. For example, when you learn a new physical skill, like a complex dance move, it's not just your muscles slowly adapting. It turns out your ability to rapidly learn and adapt, even in purely physical tasks, comes from explicit cognitive strategies. You use mental imagery, you rehearse the movement in your mind, and you consciously evaluate novel solutions. Motor learning is a cognitive hack. This means our models must now account for the synergy between high-level thought and the low-level motor system, blurring the line between mind and muscle.
Question 2. How do we act together? Joint action. Most of the time, we aren't acting alone. We engage in joint action, moving heavy furniture, playing in a band, or dancing the tango. This isn't just two individual actions added up. It requires shared intention, and that opens up a huge debate. Philosophers propose highly demanding ideas. They argue we need robust theory of mind, the ability to fully understand our partner's beliefs and desires, just to act together. But critics ask, does a child or an animal need advanced reasoning to coordinate? Probably not. This has led to minimalist accounts, which focus on real-time coordination through simpler mechanisms. Emergent coordination, like automatically falling into step with a walking partner, and goal-directed coordination, where we track our partner's actions and monitor progress toward the joint goal. We coordinate through simple mirroring, joint attention, and shared task representations. It's a battle between complex thinking and elegant automatic cooperation.
Question 3. The feeling of control, sense of agency. Finally, we arrive at the most intimate question. What gives you the subjective experience of being the author of your actions? Why do you feel like, I did that? That is the sense of agency. This feeling isn't some magical single switch. It's a rich system built on multiple mechanisms. The most important one is low-level comparison. Your brain constantly compares the predicted result from its motor command, the efference copy, with the actual sensory feedback it receives. If they match, your brain confirms, yes, I am in control. But agency is also influenced by high-level cues, like how fluent or easy the action selection felt before you started. The neural basis for this crucial sense of self-consciousness isn't one place, but the connectivity between the frontal motor areas that initiate movement and the parietal areas that monitor the resulting sensory events. These ongoing studies into control, cooperation, and consciousness are the challenges driving the next generation of action research, and they are fundamentally changing how we understand what it means to be an agent in the world.
Our journey through action theory reveals something profound. Agency is not just a human feature, it's an evolutionary masterpiece. The evolutionary ladder and the AI challenge.
It's proposed that biological agency evolved across species, from simple goal-directed activity in ancient creatures to intentional agency in mammals, and finally to our uniquely human socially normative agency, the ability to act according to shared rules and moral standards. This brings us directly to the future: artificial intelligence. For decades, AI has excelled at planning and problem-solving, creating systems with sophisticated action control. Yet there's one massive hurdle. While AI can represent goals, its goal-directedness remains extrinsic. It is imposed by its programmers, not generated internally. The moment we manage to create an AI with genuine intrinsic motivation, a goal that arises from within the system itself, we face the ultimate ethical question. Should these increasingly sophisticated agents be considered moral agents? Do they possess the necessary autonomy and self-control to be held morally accountable for their actions?
The unifying core. Finally, our research into action has opened doors to other fields, from understanding why we cooperate, pro-sociality, to how we form collective memories. But despite all these advancements, from Aristotle's philosophy to advanced neural network modeling, the most fundamental question remains unanswered. We've seen the incredible variety of action: routine, deliberative, mental, joint, habitual, and intentional. But is there, beneath this breathtaking diversity, a single, shared, common core of properties? Is there one unifying blueprint that defines all action? This deep mystery is the challenge driving the next generation of cognitive science. Until we answer it, the simple act of reaching for a coffee mug will remain the most complex, predicted, and elegant operation your brain performs every single day.
Thank you for exploring this fascinating topic with me. If you enjoyed discovering the science behind your every move, please like this video, subscribe to our channel, and let me know in the comments below. Do you think AI can ever truly achieve intrinsic moral agency? See you next time for our next cognitive adventure.